But it's an international group of people that will all highlight instances where more testing simply means it makes money. It saves money. It makes the project more advantageous. First example of that will be given by David Terr, Thurber Engineering. David, the floor is all yours.
Good morning, everybody, or at least good morning from the west coast of Canada. Glad to see that everybody's been able to make it here. So today I'm going to talk about the Pitt River Bridge Design Build project. And you'll notice the titles got swapped around a little bit, and it's pile installation, testing, and design. There's a bit of a reason for that. And so a bit of an outline here. I'm going to talk a little bit about the location, project specifics, some of the design build requirements as they're relevant to the program, geotechnical conditions, design concept, and then this whole business of pile installation, testing, and design, and then we'll talk a little bit about the savings. And the little view on the left is kind of the confined area that we're working in, where the testing will be focused, and we can see one of the former bridges on the left-hand side. And probably notice there's quite a bit of settlement between the approach fill and the first pier. So where are we? We're in, you'll notice there's the border down there between Canada and Washington State, and the little red circle shows where the bridge is. It's this Highway 7 crossing of Pitt River, so just to the east of Vancouver. And the former bridges were swing span structures. The downstream bridge, so that's at the towards the bottom of the page, was built in the early 1900s. The upstream bridge was constructed in the late 1970s. And one of the things that happened was the upstream bridge had settled in the order of about 150 mils, so 6 inches, and the approaches in the 500 mil range. So there was some real problems with the bridges, particularly with the swing spans, which caused a lot of traffic problems. So both bridges were nearing their end of the design life, and so the new bridge was proposed to be built between the two existing structures. Here we can see the East Tower with the little red circle around it, and we can see preload fills and so on at the where the approach fills are. So if we look at what the design build requirements were, we've got one of the primary ones was the foundations were to be installed into the underlying glacial and interglacial deposits, and the driven piles were to require at least one dynamic load test per pier and abutment element. And finally, the existing structures were to remain in place and operational during construction, and really that meant that the swing spans had to keep working. So the design build requirements of the bridge was to be built in accordance with the Canadian Bridge Design Code and the British Columbia Transportation Bridge Standards and Procedures Manual, as well as a supplement to the bridge code. And what was really relevant was that from a design perspective for compression, looking at using resistance factors of 0.45 for CPT based in design, 0.5 only for high strain dynamic testing, static load testing. We're looking at a 0.6 with testing in the same direction, but no instrumentation down the pile. And then this could get as high as a 0.7 with a static load test if we could separate toe and shaft resistance. Geotechnical conditions here, we've got a CPT that was done by the team comprising Hewitt and others. But we've got fill over a sequence of silty sand with clay seams down to 20 or so meters over these lower silts and clays, and that are fairly compressible. And then we've got till down in the 96 to 100 meter range. And here's a kind of a concept design concept. So the artist rendition of what the bridge would look like, basically a cable stayed structure, although the reference concept had included a cofferdam. The design team preferred to stay away from the cofferdam because of fish windows and so on, so to try to stay out of the river as much as possible. And the intent was to go with large diameter driven piles for ship, and that'd be gravel barge impact. The former bridges were not designed for any kind of impact. You'll notice the east tower was at the riverbank and the west tower up in the channel. Our focus is going to be at the east tower. And a key part of it was this, the size of the crane that was going to be used was very much a part of the conversation. And then what hammer was available locally to use on the project. So for the design and so on, there was quite a bit of existing data. There was historical investigations, including the 1973 or static loading test that had been done in 1973. The owner had also conducted what we call an indicator pile program in 2005, and that included dynamic monitoring. And the owner had also provided lots of shallow CPTs, and by shallow I mean CPTs to 30 meters, but remember that we have a contractual requirement to install the piles to essentially 100 or so meters. There is one shallow, one very deep test hole to 100 meters to at least show where till was. During the pursuit, I guess the other part of it was we convinced our client that it would be beneficial to push a couple of CPTs, so a CPT at each abutment location on the shore, to try to get to till or as close as possible to till to confirm that the conditions are consistent across the river. And that was fairly successful. So if we look at the testing data from 1973, we had two piles were installed. One was installed to about 36 meters, and the other to 55 meters. The piles were 610 mil by 12.7, so that's 2 feet by ½ inch. They were open toe. The piles were installed by impact driving using an MKT 11B3 double acting air hammer. Fairly small hammer. They were cleaned out and filled with concrete. I think nowadays we probably wouldn't clean them out all the way to the toe, but that was what was done at the time. We can see here the installation record where there's stops for splicing or stops for measuring other things during the test. So there's quite a bit of setup occurring between or during the installation process here. And something that this tool was developed a little bit after the testing was done. But one of the things we want to show here is that the hammer that was used was relatively small. This is a tool that was reported in the DFI magazine in 2017. And if we had used a pile or a hammer that was more typical for that size of pile, we would have probably used a diesel hammer, an APE D30 or something like that. And what we have on the vertical axis here is pile energy divided by the steel area, D over T on the bottom, so kind of a proxy for the inverse of the solidity ratio. And if we'd had the APE hammer, for example, we'd be at about 3,700, so in a nicely in the green area. Anyway, we'll come back to this. And looking at the load movement response, we're going to call that something around 3,600 kilonewtons for the deeper of the two piles. And if we take that test data, we back out a beta, an effective stress beta for the piles, we get a nice fit with a beta of about 0.15. So we're not trying to get a lot of fine-grained resolution here, but rather an overall fit to our data. And now when we look at what was done then in 2005, so these pre-bid indicator pile, or there was a pre-bid indicator pile, it's a 1067 by 19 millimeters, so 42-inch by 3/4 inch, again, open toe. It had a doubler plate at the toe. The doubler plate was on the inside of the pile, and that was intended to mitigate the risk of toe damage. The pile was installed to 93 meters approximately in 6 days with an APE D62. So it looks like the APE D62 is better matched than the MKT hammer was with the 610 pile. And then driving was finished at 7 days later with an APE D180, and that the delay was simply waiting for the hammer to show up on site. Key note from this one was the pile cord during driving. The 610 piles that we installed during production work typically would partially core, so the soil might be down for a 60-meter pile, the soil might be down 20 meters from ground surface. Looking at a end of drive wave trace, so I've got my force on the top and ZV on the bottom. We can see we're mobilizing the pile toe at end of drive for that test, and we're getting about 37 MPa over that steel area. When we do a restrike test here, the blue being the early blow and the green being a later blow, we're just not getting the energy down to the toe anymore with the test. So the takeaway is we're not fully mobilized here. We have the upwave, which is just the F minus ZV over 2. And again, the black trace being end of drive, so we're mobilizing the toe, and by the time we get to the other, the restrike test, we're not. What we do know is we were mobilizing in the range of 16 meganewtons in the shaft on the restrike, and if we take, we'll come to that in a second. Anyway, and if we look at what was going on with the hammer here, with the D62, we're in that nice green spot on our little chart here, and by the time we get up into the D180, we're up in the red zone, and the red zone has two things that are challenging with it. One is this damage, and when I talk about damage, it's a buckling, local buckling type of problem. And I think what it's telling us is the pile is the limiting part of the equation, so we're not able to get all the energy down to the pile toe. When we're below about the 6,000 mark here, or when we're around the 6,000 mark, we're fairly well matched. And then when we're below, we're not necessarily able to get all the or that much energy down the toe, again, depending on L over D and so on. But it's intended as a screening tool. So if we look at the data that we got there, we fit it with just scale up our shaft resistance. With the beta 0.15, the shaft resistance from signal matching matches up reasonably well. And we can argue, we would argue that we probably have a shaft and combined shaft and toe resistance of about 21 meganewtons for a 100-meter long pile at this location. So now if we then go towards our design build concept, we decided that we were going to size the pile using the API criteria for wall thickness. So that's my D over 100 plus 6.35 millimeters, or D over 100 plus 1/4 inch. We thinking about what the crane can lift, what we can drive with that APE D180. And again, that's where that screening tool becomes fairly handy. And some cones were actually pushed into the till, which meant doing drill outs and so on, which if you think about drilling down 100 meters, it's quite a feat. And what we were able to do with the cone is push maybe only 100 millimeters or so, so 4, 6, 8, whatever, 10 inches. And we were getting tip resistances in the range of 25 to 37 MPa before we were told we had to stop or we would be breaking the rods. So that was nice in that the 37 MPa, or we were getting numbers with the cone that were matching what we were getting from the high strain dynamic testing on the steel shell. So here's just a slide showing what it looks like when trying to walk the Manitowoc crane into the site, and you'll notice the modular block wall on the left-hand side where the approach fill toe had to be cut back, but site access was quite difficult here. So we ended up picking a 6 foot by 1 inch, so 1829 by 25.4 steel pipe. The pipe, we decided to go with the doubler plate as was done with the indicator pile to protect the toe, and I think it was a good choice. The pipe was delivered in 12-meter long segments because that's what we could lift. And doing a drivability study with the D180, we felt we could get somewhere up in the range of 2100 meganewtons during a high strain dynamic test. So, and again, where we see where we are with the pile, it would suggest that we're now the pile is, or sorry, the hammer is the limiting factor, and again, the line off on the side here is kind of a damage line. So we if we take the beta value of 0.15 and just scale up for the size of pile, we'd be looking at a shaft resistance here now of 28 to 30 meganewtons. And toe resistance, just based on annulus, using that 25 to 37 MPa, and all simple math here, nothing fancy, we're in the 7 to 11 meganewtons. If we were to test statically, which we ultimately did, the argument would be is we could go to Randolph or somebody and use this QB01, so at 10% of the diameter of 0.2 for what we would call a coring condition, that would give us a toe resistance in the range of 13 to 20 meganewtons. So combined, we are in the range of 35 to 41 meganewtons with the dynamic test, or at least that's what we think what we could do. And that requires superposition. And if we were to test statically, we felt we'd get somewhere in the range of 41 to 50 meganewtons. So the decision was to move forward with a static test. Here's a schematic of the eastern pier on the shore. And the idea was we'd use a production pile as our test pile. So that's the pile 5 in the middle, and it's purple. And the intent was we would install pile 1 over in the top right here, then pile 5, and we would follow with the installation of the reaction piles. So that's piles 3, 4, 6, and 7, and then proceed with the installation of the other piles. Now, and pile 1 would be subjected to more than one restrike test with the intent of using that as a guide to indicate when we should conduct the static test. So when the pore pressures would be sufficiently dissipated, or when there's sufficient setup. And the concept was, if the static loading test was not satisfactory, the fallback would be to install piles at the dashed line, locations of the dashed lines, and hopefully without having to make the cap bigger and so on. Anyway, that was the wish. And here's just a couple of photos looking at installation. I think we're installing pile P1 in, I'm not totally sure on which pile that is in the left-hand photo, and then we're installing the reaction piles on the downstream side of the test pile. So the test pile is right in front of the crane on the right. So looking at installation records here now for the test pile, that's our black trace. The piles were vibroed into nominally 60 meters and then impact driven. And again, we can see the D180 is matched up fairly nicely with the pile. We achieved our termination criteria just below 100 meters with the test pile. And looking at an ended drive test, the wave traces here, the force on top and ZV down below, we see very similar or a very similar response with pile P1, so the pile we were subjecting to multiple restrikes, and our test pile, so that was somewhat comforting, and we're engaging the toe. By the time we go and do a restrike now on pile P1 at 6 days, that's our green trace where we can see we're getting some energy down to the toe, but we're not really engaging it. And then by 51 days, not at all. So looking at the upwaves, we'll cut off the upwave on the vertical axis there. Anyway, looking at our upwaves here, we can see again the two upwaves for the P1 and P5 look very similar. And again, we can see this progressive setup with the other couple of blows, but we're not getting energy down to the toe. So here's looking at the shaft or the resistance mobilized with depth for the different tests. P5 and P1 fairly similar. P1 at 6 days being the green dash line, and P1 at 51 days, and we're mobilizing just shy of 21 meganewtons, which lined up with our drivability study. If we then go and apply superposition, which we kind of decided we had to do, we're looking at about 28 meganewtons for the shaft and 36,500 kilonewtons combined. But I guess the thing that kind of threw us was the distribution of resistance looked quite different from what we were expecting. So that was a little bit worrisome for us here. So the green being what we would get from either scaling the 1067 test pile data, the beta would have been very similar. We went ahead and did a static load test. We saw the reaction pile, what they look like on the cover sheet here, and the test was done at 78 days based on our forecast from the restrike tests. We ran the test up on day 1 to just over 30 meganewtons, and it was really to develop confidence in the method that we were using to run the test. And then the second day we ran it up to 45 meganewtons. You'll notice there's a little blip just before 40 meganewtons, and that's because we stopped to shim. We were expecting a lot more movement with the pile than we got. Here we ended up with under 90 millimeters, so what's that, 3.5 inches? So we're down in the 5% of the diameter type of displacement number. So the numbers aren't or are much more than, or the movements were smaller than we anticipated. So again, a very happy outcome. If we looked at the factored resistances that we got from the 3 approaches, so static analysis, and we're being a little optimistic here, but if we take the static analysis, we would have got a factored resistance of about 15.8, call it 16. High straight dynamic testing with superposition. Remember, we had 36.5, so we're in that 18 meganewton range, 18.5. Without superposition with that hammer, we're down at 10.5. So there's a real motivation to be smarter about what we're doing with high strain dynamic testing, and whether or not we do superposition, but we leave a lot on the table if we don't do restrikes. And with the static loading tests, we got ourselves up to 27 meganewtons. Our target was 24, so we're quite comfortable with what we got, and that allowed us to not have to put in the 2 extra piles. So what were the savings? Simply from a steel perspective, now you'll notice here, I say 4 piles measuring 1829 by 24.4, and that's because the piles, even though they were ordered as 25.4, they were delivered as 24.4, but we reduced a bunch of steel, 36 splices, and the splices take about 14 hours or more to complete, so there was a lot of elimination of extra work. That meant getting rid of all the delays, or a lot of delays with ultrasonic testing, because it seems like there was a lot of additional work that had to be done with that, which meant delays during installation. Their savings of crane time. Just a ballpark number, the piles are worth in the range of $600,000 Canadian, so 460,000 US, just using the 1.3 conversion. So total savings for deleting 4 piles or not installing 4 piles on the bridge towers was about somewhere in the range of $2 million. Doesn't sound like a lot, but it's 20% on the foundations for the bridge towers. Now, the reaction frame would have been, we haven't included the price here. There was a lot of steel involved. The sections were 3 meters deep, but the reaction frame has been reused on a number of projects. So the cost, it's not a throwaway cost. I don't know what the number is. It's probably, to run the static test, would have been $500,000, maybe more. So, the net savings may be a little bit less, but that's kind of where we are. So with that, I'm done. Thank you.
Thanks, David. Thanks for a very interesting presentation.